Hi and welcome to this presentation on computing paradigms. So today we'll be discussing all of the computing paradigms, that is distributed computing, grid computing, cluster computing, utility computing and cloud computing. So let's get right into it. So what is computing? Computing is the process of using computer technology to complete a given goal-oriented task. So the computing paradigms are the methodologies or approaches to solving problems using computer technology. Over the years, different computing paradigms have been developed and used, each with its own unique features and benefits. Some of the most common computing paradigms include distributed computing, grid computing, cluster, utility, and cloud computing. Each of these paradigms has its own specific goals and methods for achieving them, and they are often used in combination to solve complex problems. So, firstly, let's look at distributed computing. The distributed computing refers to a system where processing and data storage is distributed across multiple devices or systems rather than being handled by a single device. We have multiple devices and we will probably have a service connecting it, and this configuration will be in connection with a network. It's often used in scenarios involving large data sets, real-time processing, or the need for geographic distribution of resources. So now let's look at the benefits of distributed computing. First of all, scalability. That is the ability to handle increasing workloads by adding more resources. Again, it's reliable. So reliability is a benefit. And distributed computing is really flexible too. And another benefit will be fault tolerance. That's the redundancy and fault recovery mechanisms. Even if a single system or server happens to malfunction, because of redundancy and because of a number of other devices, we can like tolerate the faults. Even though there might be some problems, we can compensate for that. Another main benefit is performance. So improved processing speed through parallelism. And again, we cannot forget about cost efficiency. So, even though it has a couple of benefits, there are also some challenges we might have to address if we are planning to go with the distributed computing. So, number one is network communication issues. There is could be latency issues, and could be there also could be bandwidth issues. We'll probably need a greater bandwidth to connect to all these devices and to maintain that level of communication. Again, data consistency is a problem. Maintaining data integrity across distributed nodes. Synchronization is another problem. We have to coordinate the actions between different nodes. And also security is a problem always. So you'll have to ensure data privacy and authentication. So now let's look at the applications of distributed computing. First of all, we have content delivery networks use distributed computing. For an example, we could say Netflix or Hulu or something like that. So CDNs distribute web content across multiple servers located in different geographic regions. This reduces latency and accelerates the delivery of web pages, images, videos, and other contents to users, improving the website performance. Another example is financial services and trading. Like high frequency trading platforms, they use distributed computing to process the vast amounts of market data in real time, enabling quick decision making and trade execution. The forecasting is another area. Weather prediction models require distributed computing to process complex atmospheric data and generate accurate forecasts. Multiplayer online gaming leverages distributed computing to serve the large number of players interacting in real time. It could also be used in managing game state, matchmaking, communication between the in between players, and telecommunications. These networks that allow communication between devices over long distance, such as your telephone networks, your cellular networks, or other simple computer networks as well. So up next is grid computing. Grid computing is a computing infrastructure that combines computer resources spread over different geographical locations to achieve a common goal. All unused resources for multiple computers are pooled together and made available for a single task. Organizations use grid computing to perform large tasks or solve complex problems that are difficult to do on a single computer. It's like spread over the whole globe, you could say, in a way. So, how does grid computing work? Well, grid nodes and middle layer work together to perform grid computing tasks. In grid operations, there are three main types of grid nodes that perform the different roles. First of all, we have a user node. A user node is a computer that requests resources shared by the other computers in the grid computing. Then we have a provider node. In grid computing, nodes can often switch between the role of a user and a provider. The provider is a computer that shares its resources for grid computing. And finally, we have the control node. A control node administers the network and manages the allocation of grid computing. The middleware that runs on control nodes. When the user nodes is the middleware checks for available resources and assigns the task to a specific provider node. Again, there are three types of grid computing. We have a computational grid that consists of like high performance computers. It allows researchers to use the combined computing powers of computers. Researchers use computation grid to perform like resource intensive tasks such as mathematical simulations. Then we have scavenging grid. A scavenging grid, it refers to a component or mechanism that helps manage and allocate unused or idle computing resources within the grid. The term scavenging implies that these resources are gathered or reclaimed from systems that are not currently active, using them for primary tasks. And lastly, we have a data grid. A data grid, as the name implies, it connects multiple computers to provide a large data storage capacity. So, what are the benefits of grid computing? Of course, high performance, like by harnessing the power of multiple resources, grid computing can deliver high performance computing capabilities. Second one is collaborations. Obviously, grid facilitates the collaboration among geographically dispersed researchers and institutions. Like researchers can access and share data and coming resources, leading to more efficient collaboration on research projects. Well, cost too. Like grid computing works with existing hardware. You don't have to go and buy a new hardware. Like we can reuse the existing computers, so we can save cost there. And also scalability. Like we can scale it up or scale it down based on demand. We can accommodate larger workloads if need. Like there is a like element of flexibility while we discuss about grid computing. Well, there are some challenges too for grid computing, like administrative overload. Or it's like we have to coordinate and administrate grid environment. Like there is a lot of configuration, monitoring, and maintenance, and complexity. Like building and managing a grid infrastructure, it can be complex. Like there is a diversity in hardware and software. Like interoperability among different systems can be quite a challenge. Again, as with distributed computing, like the security and privacy issue is paramount here. Like it involves sharing resources across organizations. There is security and privacy concerns here. Like data transfer between resources must be secured, or like you'll have to prevent unauthorized access as well. Speaking about data transfer, like data management is another challenge. Sharing and managing data across different locations can be complicated. It will require like data replication techniques, synchronization, and access controls. So those are some of the challenges of grid computing. Now let's look at the applications. Like as I said before, like scientific research and simulations, this is where we use grid computing. Climate modeling, maybe protein folding simulations, nuclear physics simulations, astrophysical research. Like these applications often require massive computational power. Grid enables researchers to access and share their resources for these calculations. Another thing is oil and gas. Like it enables the geophysicists and geologists to analyze data from multiple sources to look at potential oil and gas reserves. Astronomy, as I've said before, and like educational research institutions, like universities and academic institutions, they can collaborate, like allowing their students and researchers to access this distributed resources. Also, like large scale data analysis, like big businesses, like businesses, MNCs around the world, like they can process and analyze large data sets and gain insights for their decision making processes. Let's now quickly go over the remaining computing paradigms. So, up next, we have cluster computing. Cluster computing is a type of parallel computing or distributed computing that involves the use of multiple interconnected computers or servers known as nodes or cluster nodes to work together as a single integrated system. These nodes are typically connected with a local area network and are designed to collaborate on computational tasks. They are in close proximity, they'll be very close and integrated. That is the difference between grid and cluster. Like these are very, like they are in the same building, I should say. Benefits. Let's talk about the benefits of cluster computing. So first of all, high performance. So, like we can have a great deal of computational powers by combining the processing capabilities of multiple nodes. Scalability. It's really easy to add more nodes or resources as needed. Again, load balancing. Cluster management software can distribute workloads evenly across multiple nodes, ensuring that efficient resource utilization and preventing bottlenecks. So, like if any of the cluster, if any of the nodes is having experiencing too much traffic, we can spread it out. And high availability. It can provide like continuous and reliable services being by using redundant nodes and failover mechanisms to prevent downtime and data loss in case of failures. Now let's look at the challenges. First of all, it's the configuration is quite complex. Setting up and managing can be complex. Like you have to, it involves hardware procurement, software installation, ongoing maintenance. Maintenance is a big key. Again, resource management. You have to efficiently allocate and manage resources in a cluster. It's challenging. Yeah, particularly when we deal with heterogeneous hardware, it's different types of hardware. Power and cooling, like large clusters consume significant amounts of power and generate heat. So, yeah, cooling solutions is something we'll have to look when we talk about cluster computing. So, applications mainly used for weather modeling and like image processing, for image enhancement, segmentation, yeah, compression, recognition, retrieval. Also, data miners use it. Like we can extract useful information from large and complex data sets as well. Okay, so we have now reached utility computing. Let's look at more about utility computing. So, utility computing is a model in which the computing resources, such as processing power, or storage, and network bandwidth, are provided to users or organizations on a pay-as-you-go or a metered basis. Like it operates on the principle that computing resources are treated as a utility, much like electricity or water. The users are billed for the actual amount of resources they consume. So the benefits are cost efficiency. Like we are only billed for the resources we use, so it's relatively cheaper than like maintaining on on-premises hardware. It could be underutilized, but here it's like we are paying for what we use. Again, scalability, like users can simply like scale their computing resources down or up by matching their fluctuating workloads. And like we just have to make sure that we have the necessary capacity at peak demand, and we don't have to over provision for like the quieter periods when the workloads are not that much. So there are a couple of challenges. First of all, reliability. Like customers may lose access to the computing resources they depend upon if the service provider faces any problems. So this can cause disruption. Again, security. Like the service provider is responsible for protecting us. So yeah, they may not have this adequate security measures or policies in place. So that is concern. In control, like the customers have less control over the computing resources. Like everything is owned and managed by the service provider. So the customers may not be able to customize or optimize their resources according to their needs. So finally, we move on to a last computing paradigm, that is cloud computing. So, cloud computing is a technology that allows individuals and organizations to access and use the computing resources such as servers, storage, database, networking software, and more over the internet. Instead of owning and maintaining physical hardware and software, users can rent or lease these resources from cloud service providers, CSPs, who host and manage them in data centers around the world. So the benefits are scalability, of course, and cost efficiency. Just like utility, users can avoid the upfront cost of purchasing and setting their own hardware. Instead, they can go on a pay-as-you-go basis. It's pretty reliable. They have high levels. They offer high levels of uptime and redundancy, reducing the risk of service interruptions and data loss. Security too, like most providers, they invest heavily in security measures and compliance certifications to protect their customer data. It's pretty accessible. You can access it from anywhere around the world for so this allows remote work and collaboration. But the challenges are vendor lock-in. Like if you want to move data and applications to the cloud, then it can create a vendor lock-in, making it challenging to switch providers, like switching between providers or bringing services back in-house. If you want to migrate from the cloud back to on-premises, so that is an issue. So to mitigate these risks, organizations can adopt like multi-cloud approach or hybrid cloud strategies. Again, a skill gap is an issue. Managing and optimizing cloud, it requires specific skills and expertise. So like organizations may have to invest in training or hire cloud experts to effectively navigate the cloud landscape. In network connectivity, since everything is working on the internet, reliable internet connectivity is crucial for accessing cloud resources. So like organizations remote or less connectivities may face challenges in this regard. And finally, integration complexity is quite a challenge. Like migrating existing on-premises applications to the cloud or integrating cloud services with on-premises, it can be complex. So, like ensuring seamless communication and data transfer requires careful planning and often involves refactoring or adapting the application. It's quite hard. So finally, let us look at the applications of cloud computing. So big data analytics, cloud computing comes in. Like we have Amazon's EMR, or Google BigQuery, and Azure HD Insight. These are platforms as a service. So they enable the organizations to process and analyze large data sets without the need for on-premise infrastructure. Again, for ML and AI, cloud providers often offer like services such as AWS SageMaker, Google's AI platform, or Microsoft Azure's machine learning, like for developing and deploying intelligent applications. Talking about that, e-commerce platforms like online retailers like Amazon or Flipkart, like they use your cloud infrastructure for their websites, inventory management, and order processing to handle spikes in traffic during sales and promotion. And backup and recovery. In normal people, we could provide it provides a like a safe and reliable way to backup and restore our data in case of any disaster. So users can easily back up their data to the cloud and recover it whenever they need it. So in summary, we have learned that there's no single best or optimal computing paradigm for all situations, but rather each paradigm has its own strengths and weaknesses, and may be more suitable, preferable for certain tasks or contexts. Therefore, it's important to be aware of the diversity and variety of computing paradigms and be able to choose and use the most appropriate one for our needs and goals. So we've talked about different paradigms, their use cases, their features, their benefits, and the applications where they're using. So thank you very much for listening to this presentation.